By the end of today's video, you'll have a well-tuned PIDF control for your FTC robot for use of PedroPathing.
It is wanting to be able to correct itself back.
I'm Coach Pratt, and I've been teaching robotics and design for over a decade now. And today I'm going to show you how to set up your PedroPathing robot constants file so that you're ready to start tuning for PIDF. I'll show you how to tune your localization method. I'll run you through how to use the automatic tuners in PedroPathing, the different PID controllers, a centripetal force tuner, and then also some final tests so we can make sure that we actually have effective autopathing. I'll run you through this step by step, so by the end of this, you'll be able to have a robot that can consistently follow any path you give it. Now, there's a couple of prerequisites today. You're going to have to make sure you have the PedroPathing repository already installed on your computer, and you have a Wi-Fi plugin, so you can be able to connect to your robot wirelessly. You also need to make sure you have Android Studio on your device. If you're not sure how to do any of those things, I have a full video tutorial on how you can actually do all of that initial setup so you can get ready for this tuning in the links down below. Before we get into the setup, let's take a look at the initial setup that I'm going to be using as my test device today. So this is my setup for today. I'm using a holonomic drive. This is ×4 Mecanum wheels. These are Mecanum wheels from Nexus Robotics. They're quite a hard shore hardness. I believe these are almost 90A. So you're going to have quite a bit of slip on these wheels, which is going to be a really good test of the PedroPathing tools as well. I'm using the Go Build a Pinpoint computer V2. And then for my odometry pods, I'm using a little linear spring here. And this is an odometry pod from East Loop Components as well. The wheel on these odometry pods is a 32 millimeter omnidirectional drive. And I'm using 435 RPM motors that are just straight up connected to my wheels here. I've tried my best to be able to even out the weight so that I have a central weight on my device. But even if you're not central weighted, PedroPathing should have enough corrections for us to be able to set this out. So while this tutorial today is going to be going through using 2 odometry pods and a Go Build a Pinpoint, you can go ahead and follow through all of these same tutorials, even if you're using just 2-wheel, if you're using a 3-wheel, a 3-wheel plus an IMU, if you're just going to be using the encoders. The only thing that changes is on the localization setup on this. But after the localization setup, everything else will be the exact same. Just to show you how slippery this Mecanum drive is, here's what it looks like when I don't have any tuning and this is just manual drive. So this is just pushing straight forward. You can see just how much she likes to drift as it comes around. So this is what we're working with, and here's this lateral movement as well. Let's show strafing. Strafing's actually a little bit better. With how badly this thing wants to twist and turn on these tiles, even when we're just going forward and backwards without turning at all, that's how much he wants to spin and rotate. This is going to be quite the challenge for PedroPathing to be able to tune this path. So now it's time to do some initial setup for our robot. I'm going to go ahead and go to the team code folder. I'm going to open up Java, and then inside PedroPathing, we need to open up the constants page here because we're going to start changing some of these. The first thing we have to do is we have to set up the mass of our robot. So inside of our public static follower constants, we're going to go ahead and delete this semicolon, put a new line, put in .mass, and then in these parentheses, we need to give a mass weight. Now your mass has to be in kilograms. So in my case, my robot is 5.1 kilograms. It's quite light because there's not a lot going on. Yours is likely to be a little bit heavier. Finish the line off a semicolon. Now, if you don't have a large weight scale, what you can do is you can just go ahead and stand on your weight scale, get your current weight, stand on the weight scale again, pick up your robot, and then subtract the difference. Now we need to add in our drivetrain. In my case, I'm using Mecanum. If you're using something different, you might have to add in some different constraints on this. So if I go to the pedropathing.com/docs pathing and tuning setup, I'm using Mecanum. And in this case, I'm going to grab this public static for Mecanum constants. I'm going to go ahead and copy this over. And we'll go ahead and put this underneath our public static here, and we can paste it in. Now it's time to ensure that your motor names are the same. Now for me, my names are different inside of my configuration file. If your names are also different, you should go ahead and rename those now. Also make sure you have any sort of reverses. In this case, it's usually pretty common for your left motors to be reversed and your right motors to be forward. But if yours is different, you might have to go ahead and change that. Put in a semicolon at the end after our rear motor direction. Then, underneath our public static follower, we need to go ahead and add in the fact we're using a Mecanum class here. So I'm going to add a new line. I'm going to say .Mecanum drivetrain, and then we're going to pass in drive constants as our argument, which is our Mecanum constants here. So next it's time to do our localization. On localization here, you can go ahead and pick a localizer. If you are using the Pinpoint localizer, you can go ahead and follow along with these steps with me here. If you're using one of the other localizers, I'd suggest you follow through the documentation here. I'd also suggest you take a look at how I'm going to do this here because they are all pretty similar in that. Just some of the specific arguments you put in are a little bit different. So for all of them, you have to add some sort of localizer. For the Pinpoint here, inside of that constants, we're also going to add in what localizer we're using. In my point, I'm using a Pinpoint constant. So I'm going to go ahead and copy this over. We'll put it underneath our Mecanum drive. And we'll paste this in. Now, some of these things are currently going to be incorrect. First thing we have to do is set up our pod locations. Now, the pod locations one is kind of the offsets for it. It could be a little bit confusing. If you looked on my robot, this is the same setup. The rev control was at front, and I had our forward or our X pod on this way and our strafe pod or our Y pod at this direction. We need to calculate the offset from the center of our robot to the center of the dead wheel on this odometry pod. And the same thing from this center robot to the center of the dead wheel on this pod here. So our X pod and our Y pod. So let's go ahead and put in some of these now. So I've measured the distance from the center of the robot over here. You can either do it in CAD or you can do it with a tape measure, your choice. And these offsets have to be in inches. So in my case, I measured it in millimeters. So I'm doing negative 182 divided by 2.54, and that will convert it in inches. And my strafe pod X was negative 196, divide that by 2.54. You also select your distance unit at this point. And in my case, I'm going to be using millimeters. I personally find that makes life a little bit easier. For your hardware map name, you have to make sure this is the same. When you have your Go Build a set up with your encoder, I have it set up as a Pinpoint when you scan for it because that's a default name. I've also got my Pinpoint plugged in on the ITC port 3. Now, for the encoder resolution, if you're using one of the Go Build a odometry pods, you can go ahead and select whichever Go Build a pod you want here, whether that is a dot Go Build a 4 pod or a dot Go Build a swing arm. But because I'm using a custom encoder, I have to put in something a little bit different here. So rather than putting in my encoder resolution, I'm going to say dot custom encoder resolution. And the East Loop Components encoder uses 4,000 ticks. And we'll divide that by the circumference of our wheel. In this case, it is 2 times math.pi times 16, which is the radius because my wheels are 32 millimeters in diameter, 16 millimeters in radius. Now, one thing I'm not sure about here is for custom resolution, is this in inches or in millimeters? I've been putting it in millimeters and it seems to have worked for me, but perhaps I am incorrect on this, in which case, please let me know in the comments down below. And then last up, you need to set your encoder directions, which we can do our first actual test to figure out what our encoder directions actually need to be. So on our driver station, we're going to select teleop, scroll down to our tuning folder, and we're going to initialize. And now using the left and right bumpers on our controller, we're going to use the D-pad to select localization, right bumper to select, use the D-pad select localization test, right bump to select. And here, we're going to print our telemetry. So we're going to go ahead and press play. And what we would want to do is we want to push our robot forward and watch our X and Y values. What should happen is when you go forward, your X pod should increase. And as you go left, your Y pod should increase. If that is the case, they should be both orientated forwards. If not, one of them is going to have to be reversed. In my case, my forward encoder direction is forward, but I do have to be reversed on my strafe encoder direction. Next, we're going to go ahead and add in our localizer inside of our follower. Above everything else, I'm going to set in dot pinpoint localizer, and I'm going to pass in the localizer constants. Now, if you're using something different, you need to make sure you don't use the pinpoint localizer. I believe there'll be a different method that you're calling in here. So now let's verify these things work. I'm going to go ahead and connect to my robot's Wi-Fi network again, and I will build this code over on here. And let's run the same test. We'll run that localization test, and we'll verify that our X and Y values are indeed increasing and decreasing as we move forward and left and right. So with the robot up and connected, you can now go ahead and either decide to set this up on your driver station, or I'm going to use panels. Underneath the panels dashboard, I'm going to select teleops. I'm going to select tuning / PedroPathing, and I'll go ahead and initialize this. So now using my gamepads, I'll have to look down on my screen here, select right bumper to grab localization, right bumper for localization test, and we'll go ahead and start this up. And we can see on telemetry, let's verify with that initial setup done and the localization setup done. It's now time to start testing and tuning our automatic tuners. And PedroPathing has 4 different automatic tuners that you need to run specific tests on, and then grab values from. The first one is the forward velocity tuner. And the purpose of this test is to test what is the maximum velocity that your robot achieves when you move at full speed forward. You gotta make sure you have enough room because by default, this does 48 inches forward. The longer you run this for, the more accurate your test is going to be as well. So effectively, your robot's just gonna drive real hard forward at 48 inches and then stop. So to run this, you wanna make sure you have a fully charged battery. I don't have a fully charged battery here, so some of my values here might be slightly incorrect when it comes time to actually run this. So make sure you always got a charged battery. In my case, this is gonna be fine just for testing purposes today. I'm gonna teleops. I'll select Tuno and PedroPathing. I'll go ahead and initialize this. Now on my driver station, I'm gonna use the D-pad to select automatic, right bumper to select, and we're gonna choose our forward velocity tuner. Right bumper, select this again. It's gonna throw some stuff up. We're not gonna play this yet. I'm gonna grab my robot. I'm gonna bring it back to the start of my field here, and I'm gonna make sure I have this parallel lined up straight so this thing can drive forward, because it's not going to drive perfectly straight at the moment. Now, what we're going to be looking for here is down in the telemetry section panels, it's going to print a specific X velocity for us here. If anything ever goes wrong, you can press B on your D-pad to be able to stop the robot. So let's go ahead and run this. So when I click start, it should drive forward inches, but we're going to change cameras here so we can actually see what our robot looks like. So I'm going to press start and get ready to stop it if I need to. We see that we ran off our field a little bit there, so let's try that test again. Because the wheels I'm using are not very grippy at all, I really need to do quite a bit of tuning with my lateral velocities on this. So I've changed up my field a little bit here, so hopefully this doesn't run off. Let's go ahead and run this one more time. Beautiful. So that is a far more accurate test. And we look at our desktop here, we now have a forward velocity section. So I'm gonna go ahead and grab this, I'm gonna copy this. And inside our Mecanum's constant section, we're gonna delete our semicolon there. We're gonna add in a new line called .x velocity. And inside that, we'll paste in that value that we got from our test there. Now, as far as I'm aware with panels, I could be incorrect on my understanding of this. But at this point, if we press A, we should be able to temporarily set our constant for X velocity to whatever value just popped up here in our forward velocity. And then as long as we don't turn our robot off, our robot should remember that inside of that X velocity, so that once we've added in our section here, it will temporarily hold this number. And then when we build our code again, it will keep track of this. So after we've pressed A to confirm that we've actually set that up, we can go ahead and stop our program and we do our next test. Now this next test is lateral velocity, and this is doing the same thing as forward velocity, but it's checking your sideways. Now because I'm using these Nexus Robotics wheels, this one I typically have to do quite a bit because I do not have a lot of grip on the floor. Again, by default, it does 48 inches. The longer that you run this for, the more accurate your tests are going to be as well. So we're gonna go ahead and pick our robot back up and we'll set it up. And by default, this robot's gonna go to the left. So in my case, this is how I'm gonna get this set up. I also like to offset mine a little bit because it likes to go on a bit of an arc in these tests before they're tuned. Now inside of our driver station, we'll initialize again. We'll come down to automatic tuners, right bumper to select, come down to lateral velocity tuner, right bump to select. And then the same thing, once we press start, it's gonna attempt to go 48 inches to the left. On our panel section here, we're gonna try to keep track so we can run this. Again, press B if you have to stop at any time in case something goes wrong. Let's switch cameras over here and let's go ahead and play and see what happens. So I ran off the edge. Let's set that back up again, and we'll try that one more time. Surprisingly, I'm actually managing to stay on today. So we're gonna have to run that one more time. And you'll realize this is really common in robotics and in PIDF tuning, is that sometimes you really gotta play around with your values a lot. And not quite a perfect test. I'm going to move this one more time because you can see that our lateral velocity is not near as fast. We get a whole whack load of slippage. Okay, and we finally got a test that worked. Looking at our point here, we have our strafe velocity. Our strafe velocity is quite a bit lower because we just so much slippage on these Nexus wheels. So the same thing, I'm going to come down here. I'm going to go ahead and press A on my controller so I can temporarily set this. Put in my .y velocity. Go ahead and paste in that value we have and put in our semicolon. Next up, we have the forward 0 power acceleration test. And what this one's going to do is it's going to drive your robot forward roughly 30 inches, then cut the power and see how long it takes for your robot to slowly drift until it stops. This is effectively a brake tuner for this, and this is quite critical for setting up more accurate pathings in Pedro. We're going to go ahead and set our robot up so that it is facing forwards. And it's going to want to move forward about the length of one tile. So on driver station, we'll initialize. We'll go down to automatic testing, go down to forward 0 power acceleration tuner. And again, just like on panels, we're going to watch this. So let's go ahead and play this. And we'll go ahead and grab our values off of that. So let's look at our panels dashboard here. We've got our forward power deceleration. We'll go ahead and copy this. We'll press A on our controller to temporarily set this over. Now, in this case, we are not going to add this value to our Mecanum constants. Instead, we're going to add it to our follower constants. So I'll put that semicolon in a new line. And in here, we're going to say dot forward 0 power acceleration. And we'll paste in the value that we got there. Again, make sure you don't put this in Mecanum constants. Make sure you put this in the follower constants. And the last test to run is the same as the forward 0 power acceleration, but in this case, it's going to be the lateral. So again, it's going to be want to move to the left and cut power. So let's set our robot up. So that is going to want to move to the left. Go to initialize, come down to automatic tuners, come down to lateral 0 power acceleration. And when we click play, it should attempt to run sideways. Oops. And I didn't follow my own rules. It's going to go left. So now we'll come back to panels. We'll grab our lateral 0 power acceleration. We'll head on over. And again, inside follower constants, add a new line and dot lateral 0 power acceleration and paste in those values there. So with our automatic tuners out of the way, it's now time to start tuning the PID controllers. Now, this video is not here to explain to you fully what a PIDF controller does, but for the most part, just so you can let you know, it's something called proportional control. So what a PID controller in brief lets you do is it effectively allows you to tell a motor when to go at a specific point, and you can as you get closer to the target value you want, you can proportionally turn back the amount of speed you're going to add this in. A great example of something in proportional control is something like your own body. Imagine you're going to drink a cup of coffee. As you bring this cup of coffee closer to your mouth, you instinctively, proportionally slow down the speed at which you're moving that coffee cup towards your mouth, because you don't want to move the entire speed the entire time, because otherwise you'll end up spilling coffee all over yourself. And you're going to proportionally slow down as you get closer until you hit your goal point of your mouth to be able to drink that coffee. That's the proportional component. You also have something called derivative component, which allows you to, as you get closer, it slows down some of those sections. You also have an integral component, which allows you to keep track of the drifting of errors you have. And you have something called a feed forward constant as well, which allows you to predict where motions are going to be going in the future. If you want some more understanding on how a PIDF controller works, there's some excellent videos in the description down below. Now, PedroPathing allows you to have a single PID or a dual PID system. This tutorial is only going to go through a single PID system because for most teams, this is going to be good enough. And as I always say in robotics, you don't really want to let perfection be the enemy of good enough, because most of the time, good enough will get you there. So tuning PIDs is as much of an art as it is a science. And you're going to see, and we're going to tune this together. And I'll try to give you some feedback on how I like to tune PIDF controllers as we go. But it's not going to be fully getting into the theory on this, but if you follow along, you should be able to get a pretty good aspect of this. So the first tuning we're going to do is our translational PIDF. And this is effectively going to make sure that a robot can follow a straight line without deviating laterally or left and right. So inside of panels, I'm going to go ahead and select the Pedro tuner pathing. I'm going to initialize. And under tuning, I'm going to come down to manual. And in manual, I'm going to select translational tuner. And we're going to go ahead and before we run this, inside, we are now going to actually adjust our PIDF values on the fly. So I'm going to come into tuning, come down to follower, and down to constants. And we are going to change the coefficients of translational PIDF. So here we have our p-value or proportional value. This is the most important one in this respect. We have our I value or integral, our F or our feed forward value, and our D or our derivative value. So I'm going to start by setting everything down to 0 and press refresh to load this down to our robot. If we do not press this little button or press return after entering the value, it is not going to actually keep track of these things over time. So now if I press play, what's going to try to happen is the robot is going to try to keep itself from moving laterally. So if I have no PIDF control and I come over to our webcam here, when I come up and try to push the robot, nothing is going to happen. It's not going to change or move itself at all. What we want to do is we want to see it move itself back. So now comes the tuning process. And the tuning process is as much an art as it is a science. And in all fact, it's probably more of an art than it is a science with tuning this. So the first thing we're going to tune here is our F controller. And what we want to do with the feed forward is we're trying to keep track of just how much power should we give the motors to overcome the force of friction that is keeping us on the floor effectively. So if I put in a really high value like 0.1, you're going to notice, and as I press this refresh, our robot's going to start shuffling around. That is really bad. So if I put in a really low value like 0.01, it doesn't move at all. We get a little bit of coil whine. And what our goal here is we are trying to find the value that we can put in so that we still hear coil whine, that we can hear our motors trying to move, but we do not overcome yet that force of friction. So we're going to go ahead and increase this. And what I like to do is I like to increase at the start of my PID controllers, doing really high values and really low values so we can help constrain ourselves in a little bit lower. So I might do something absurd like 0.7. So you say 0.7 is clearly too high. Let's go down to 0.2. That looks pretty decent. Let's go to 0.4. As we run this, okay, so 0.4 is still not producing anything. 0.5 is not producing anything. 0.6 does produce too much. So let's go down to 0.3. And maybe, oh, we can hear it shifting a bit. So 0.3 is still a bit too high. So let's do it at 0.25. As we run that, we're taking a look and we're hearing, are we seeing any shifting in our robot or anything like that? And as a initial final check, we can come up and give our robot a little bit of a push. And we shouldn't see any shifting or moving on this value. So this is a pretty good value for our F controller. Now we're going to go down to the next important one, which is our P controller. Again, with our P controller, we're going to start with something maybe absurdly high of something like 0.1. And now comes the time we have to actually start doing our push tests. So as we start to do this, we're going to try to push it, and the robot is going to try to correct itself back. But we always want to see that our robot is correcting itself back to its center point. So what I'm going to do is I'm going to pick my robot up and move it to a point where, oh, we can actually see we're getting a little bit of jitter there. So it's possible that my F might be a little bit too high. I'm going to get my center point here, and I'm going to push my rover. I'm going to try to see, when I push it, does it overcorrect or undercorrect in our values? And it looks like, to me, like we are getting a bit of overcorrection at 0.1. So we'll put ourselves back into that center point, and we'll go ahead and change this value down something quite a bit lower, something like 0.01. So we'll put it really low. And if we put proportion value really low, as you move this, you see that it doesn't correct enough. So now we need to try and find a value that where we can correct enough, but not so much that we overcorrect. So let's try 0.05. My guess is 0.05 is going to be too much. Oh, no, 0.05 is not enough because now we're not correcting at all. So let's do something higher. We know that 0.1 was too high, but 0.05 is too low. So let's try 0.075 and see what that does. Okay. So perhaps too high now in this overcorrection. Okay. I might tune that down a little bit, 0.06. Let's try just 0.07 or maybe 0.69. Now this one is quite a bit of a science here and quite a bit of art, but your goal is to be able to push this and it corrects itself back without overcorrecting too hard, and larger movements are going to show you whether this thing is overcorrecting too hard. In this point, we can see that it is overcorrecting quite a bit, so we're still quite high. So let's move into a low value, something like 0.6. And I'm pretty happy with this value here, because we're not overcorrecting like crazy, but it's also not terrible. Now let's go ahead and change our derivative control. And derivative is basically going to bring us slower to our center goal point. I think my feed feed forward is actually a little bit too high, so I'm going to bring this down a little bit too. So inside derivative, it's going to slow you down. So if we put on something absurdly high, like 0.9, you're going to notice that as we give this a push, it's going to try to find itself back to its position and slow itself down way too high. Let's put it down to something like 0.2. Still absurdly high. So we'll bring it down to something like 0.001. And by having in a derivative control, you'll notice that our robot is now going to try to more slowly drift itself back. If you notice from before, on the proportional control, when it tried to bounce back, it did not slowly return itself to center, but now you'll notice that it is more smoothly returning itself back. You should spend a lot more time tuning this than I do. At this point, I'm happy enough with these values of where I'm at, but you should definitely spend more time tuning this to make sure it works. And you could tune this till the cows come home. And to be honest, you just kind of have to get a good enough value. But having a really solid PID value is really going to inform these steps up. Inside of our follower constants, we're going to put in a dot coefficients. There's a new PID coefficients. And inside here, put in our dot pro for now, because you don't do it, like that's pretty low. She's going to slow down. So looking at my panels dashboard here, the first value is your P value, which is 0.06 in my case. Next, you have your integral value, which in my case is 0. And then your derivative value, which was 0.001 in my case after my proper tuning. And then my feed forward was 0.025. And I had one too many parentheses in here as well, which is why I was throwing that in there. So next up is our heading PIDF tuning, which is our lateral movement or where we're going to be pointing in a direction. So now we're going to do the same thing, but in this case, we're going to be rotating our robot. So we'll go ahead and go back to the panels dashboard. We'll initialize, come down to the manual test, and do the heading tuner test. So inside here, we're going to come down to our coefficients of our heading PIDF, and I'm going to set our proportional to 0. And we're going to do the same thing with our tuning, where we're going to try to get our feed forward to just move but not quite rotate. So my guess is it's going to be pretty similar to what we had before, and maybe we might go up to something a little higher. Looks like 5 was too much. And I know in my case, lateral forces require a bit more, so it looks like 0.25 is pretty similar in mine. It may not always be the case that your feed forward is different. So now let's go ahead and start tuning our proportional control. And again, on this one, we're going to try to rotate ourselves back. So I'm going to start with something pretty high, like 0.1. And we're going to grab our robot. We're going to try to twist it in place. And it's going to try to correct itself back to its initial heading. And it looks like 0.1 is actually probably too low in this case, surprisingly. So let's go up to something more like 0.4. And let's see what this does. So now as we give this a rotate, it's going to try to bring itself back to its heading. And that's actually pretty solid where it's getting back to its heading. So I'm pretty happy with that. I'm going to keep that where it is. We'll go ahead and do our derivative. We'll do something pretty low here, like 0.002. Go ahead and run this. Now keep in mind, your PIDF values are going to be quite a bit different than mine. And we can see that it's more slowly correcting our heading back in. And I'm pretty happy with that as well. And again, I'm not going to touch the integral control on this one. Now, underneath our follower constants, we're going to say a new dot. I'm going to stop this program because whenever panels is running, it does not play well with Android Studio and all of the recording software that I have set up. And we're going to search for heading PIDF coefficients. And this could be a new PIDF coefficients again. And inside here, we'll put in our, just like we did up top, we'll copy in those values. Now, I spent more time tuning this. So I have 0.71 as my power. I have 0 as my integral, 0.002 as my derivative value, and 0.025 as my feed forward value. I spent more time tuning this at a different point in time on this current robot. So this is more of just an instructional point to this day. And my apologies, I should have done that on a full desktop view. Now comes time to tune our drive PIDF. And the drive allows us to keep better forward and backward strengths for braking and moving straight along that path. So we're going to go ahead and update some of these as well. Now, the first thing it asks us to do is to be able to tune braking strength. Now, braking strength can really help us change how our robot moves at the starts and the ends of our path. A stronger braking strength is going to cause our robot to stop more abruptly. And a lower braking strength can cause our robot to have a more smooth stop. So the higher the braking strength, the shorter the stop period and window is going to be. The lower the braking strength, the longer that braking window is going to be. So inside our public static path constraints, I'm going to go ahead and make these new lines here so we can see things a little bit easier. Our default value is a braking strength of 1 and a braking start of 1. And the braking start allows you to change where along that path it actually starts doing that braking, whether it's at the end, whether it's 95% done the path, 70% done the path, whatever have you. It's time for us to tune some of these. So with panels opened up, I'm going to go ahead and select the tuning PedroPathing. We'll initialize this. We're going to select a manual test, and we're going to select the drive tuner. Now, the drive tuner is going to attempt to drive 40 inches forward and 40 inches backwards, and it's going to go forward, back, forward, back, forward, back. So we're going to tuning follower, and then we're going to come down to the very bottom where it says path constraints. Here's where we can start actually tuning our braking strength and our braking start for this PIDF. Now, when it comes to tuning the braking strength, PedroPathing wants you to run manual and then drive tuner. This should work if you're using a grip enough Mecanum wheel. In my experience, turning off my PIDF so I'm going to go into tests, I'm going to choose line instead. The difference between these two tests is that one has a line test and that keeps your PIDF control for your translational and your lateral movements on. The drive tuner does not. And because I have such slippy wheels laterally, I have to keep on my translational coefficient, or it will make me fall off completely if I don't have that PIDF turned on. So I'm going to keep that on personally. So we're going to come down inside tuning follower. Inside follower, we'll come down to, where is it? Path constraints. We're going to start playing with our braking strength. Now the default braking strength is 1. So at this point, I'm going to go ahead and press play on the driver station. And we're going to set a braking strength of 1, and we'll see what happens. So let's bring that braking strength down, say 0.5, and let's watch what happens. So if our braking strength is too low, you'll notice that it's trying to stop before it gets to the end of that path. If we bring it up to something like 2, it's going to have a more abrupt stop, and it's going to overshoot that path. So we might have something like a 1.5, and I'm going to stop this as I'm starting to run off because I've overshot. It'd be nice if you do this test on a much larger area. But the lower braking strength is going to make you not overshoot. And a higher braking strength is going to make you more likely to overshoot your line. So in my case, I might bring something down. Let's try what 0.9 might look like for braking strength. So I'm definitely stopping too soon on 0.9. So let's try something like 1.4. So I'm not overshooting my line, but I'm also not stopping too early. It looks like for me, that's a pretty consistent launch on that one. So now you can see that we're having some pretty inconsistent braking, or at least starting points, where we're getting off. So I'm going to stop this, bring myself a little bit more into center again here, because I like to fall off a lot with these slippy wheels. Now we're actually going to be able to start tuning that drive PIDF. The higher the PIDF you have, the more quickly your robot's going to go along the path, and the lower you're going to have, more slowly you're going to run along. So I'm going to come down here to not translational. I'm going to come to the not heading. I'm going to go to the underneath tuning follower, the coefficients drive PIDF. And I'm going to keep my feed forward. I'm going to set everything else to 0. Except for my T coefficient here. In fact, in this one, I'm actually not going to muck around with the T coefficient at all. So I'm going to come to tests. I'm going to run the line test. I'm going to go ahead and run the line. And now we're going to start playing around with that power coefficient until we're able to run our test along. So I'm going to start with something like 0.4. Looks like I might need even something maybe a little higher, 0.5. Just because I've got such slippy wheels here and I'm starting to fall off, because I didn't have a high enough power coefficient at the start. So we will run that again. because you can see that some of my wheels here aren't actually activating and I'm starting to rotate off real hard. So I can come back down to tests, do my line test. We'll go ahead and run that again. And we're going to start playing with that power. Let's see what happens when we bring that power coefficient up again. Seems to be getting more on the right track. Let's damp it a little bit with maybe a 0.001 on the differential. And that's actually starting to look pretty good. Other than our very first initial start, we're able to relatively consistently keep a line. And again, you should probably do a little bit more tuning on this. I'm going to move over here because, again, when I first start, I liked one of my wheels must have slightly different friction on it because it doesn't like to actually kick itself off right at the start. Okay, so now we're going to check our ability to actually run that line. And we're slowly drifting back as time goes by, so I might need to actually increase my translational heading tuner again, which is surprising, so that we don't spin off quite so much at the end. Okay. And even though I'm getting a little bit of bad tuning, it is wanting to be able to correct itself back. So overall, I am pretty okay with that. Once after I actually get myself started and moving up to speed after that first initial start, it seems to be okay. So I'm going to stop that. And now we're going to translate these points back in on our code here. Up under here, underneath the follower constants, we're going to say a new dot drive PID coefficients, and this is going to be a new filtered PIDF coefficients. And again, it's going to be the same thing as before, where we have our power, which is 0.6. We have our integral, which is 0.0. We have our derivative, which was 0.001. We have our t-value, which is 0.6, or our Kalman filter. And then our feed forward was 0.025. So with that drive coefficient out of the way, the last thing that we need to do is our centripetal tuner, which is our ability to follow along a curve. So we're going to do this translational here, or this centripetal. We're going to come to tuning. We're going to come down to manual. And we're going to select the centripetal tuner. And on the centripetal tuner, it's going to want to try to curve up and to the left. So we'll set ourselves up in that back left-hand corner. Down to manual, come down to centripetal tuner. Start one more time. And we're going to look at our curve here. Now, the centripetal scaling, as far as I'm aware, if you are correct, you're supposed to watch your robot drive here on the panels field. For whatever reason, my quick start, it's not actually running. I don't know why. I've tried restarting this. If somebody knows why in the comments down below, please let me know. I'm running the test as far as the documentation goes. But if you are correctly inside of the curve, you're supposed to decrease your centripetal scaling. And if you're running to the outside of the curve, you're supposed to increase your centripetal scaling. I've got such a slippery Mecanum drive here that, to be honest, it doesn't even seem to make much of a difference for me at all. I've mucked around with centripetal scaling quite a bit, but it doesn't seem to actually do anything on my drive personally. So we're going to go ahead and add in let's change the desktop view here. Inside of our follower contents was added centripetal scaling, and I'm just going to keep the default of 0.005. I believe that's what it is, yeah. Because for whatever reason, it doesn't seem to make any difference for me. This is scaling along curves, so if you're just going to use Bezier lines, to be honest, it seems to me like it doesn't actually even make that much of a difference. If you're going to be using curves, perhaps it's different for you. I haven't done any testing on grippier Mecanum wheels. So at that point, that should be all of your testing done, and now we can actually go ahead and verify that things are actually working with specs. We're going to go ahead and save this, and once we build this over to our device, we're going to run the line test again, and we can verify that it is capable of still running a line. So now we're running our line test. We should be able to come up to a robot, give it a little nudge along its lateral position, and it should attempt to correct itself back to its same line path that it was able to follow before. Now, because I like to fall off here with such slippery wheels, this is quite a challenge for mine to be able to keep itself on, especially at the start. Now, it's pretty obvious that these wheels are not great wheels for setting this up. But overall, the fact that it's still able to hold a path as well as it is, even with how slippery this Mecanum setup is a pretty impressive showing for this software. And I have seen teams have a lot more experience with far grippier wheels, have much better success in this as well. If you want access to more resources, things like CAD, things like code snippets, you can consider joining the community down below. I hope you found that a helpful tutorial in going through the tuning process for you. If you got any questions, let me know in the comments below. Otherwise, best of luck out there this FTC season.